Hello everyone. This video we're gonna go through the solution for homework 9. So let's look at the first problem 7.16. Determine the discharge in the pipe and the pressure at point B. Neglect head losses. Assume alpha equals to 1 at all locations. So for this problem we're gonna use energy equation for 3 points. So let's say first point is at water surface, second point is at point B. And third point is the outlet. So we are given the diameter in the figure says the diameter at point 2 is 40 centimeter, which is 0.4 meter. And diameter in point 3 equals to 20 centimeter, which is 0.2 meter. And we have the elevations of each point. Z1 equals to 1.5 meters plus 3.5 meters. Which gives us 5 meters, and elevation at point B, which is also point 2, is 3.5 meters, and elevation at point 3 is 0. Okay, so now we're gonna first using the energy equation between point 1 and 3 to find the velocity of the outlet. So let's write down the energy equation. P1 over gamma plus V1 squared over 2G plus Z1, which equals to P3 over gamma plus V3 squared over 2G plus Z3 plus the head loss. Okay, so from the figure we can know we don't have any additional pressure at point 1, we don't have the velocity, and we're gonna neglect the head losses. And for elevation of the point 3 it's also 0, and because the point 3 is also open to the air, so the pressure is also 0 here. So this leaves us a very simple equation, which is V3 squared over 2G equals to Z1. Okay, so Z1 is 5 meters, and we can solve for V3, which will equals to 9.9 meter per second. So now we have the V3, we can use this value and the continuity equation to find the velocity at point B. Okay, so Q3 equals to V3A3. The V3 is 9.9 meter per second, and the area of the point 3, I'm gonna use the diameter here, which is for circular pipe is pi over 4 times the diameter, which is 0.2 meters squared. So our Q is 0.311 Q cubic meter per second. Okay. So now we can use this charge to find the velocity at point B. So Q2 will equals to Q3, and Q2 is V2 A2. Okay, so V2 equals to Q3 over A2, which is gonna be 0.311 cubic meter per second, and diameter is twice of 0.3, so it will be pi over 4 times 0.4 meters to the power of 2, and this will give us the velocity equals to 2.48 meter per second. Okay, so now we have the velocity and elevation and pressure informations at 0.3, and so now we can find using the energy equation again to find the pressure at point B. Okay, so I'm gonna write down the energy equation again. P2 over gamma plus B2 squared over 2G plus C2 equals to P3 over gamma plus V3 squared over 2G plus C3. So this is still 0, and because it's open to the air as well, so the P3 is 0, and V3 we already found the value, and the V2 and Z2 we also know the information. So this equation will be P2 over gamma plus V2 squared over 2G, which is 2.48 meter per second squared over 2G plus, so the G can actually write out 2.1 and we can use first per second. The Z2 is 3.5 meters equals to V3, which is 9.9 meter per second squared over 2G. Okay, so, and the gamma, which gonna be so our P2 gonna be 11.65 kilopascal. Now let's look at the second problem. So we have a Gaussian which have a specific gravity of 0.8 flowing in the pipe as shown at a rate of 5 cubic feet per second. What is the pressure at section 2? And the pressure at section 1 is 18 psig and head loss is 9 feet between the two sections. Assume alpha equals to 1 at all locations. So for this problems, the first thing we're gonna do is convert the unit, because the pressure given here, P1 is equals to 18 psig, which is in inch. So we're gonna convert it to feet first to match all the other parameters. So 18 psig, which is 18 pound force per inch squared times 1 inch over feet. Okay, so this will give us a number of 2,592 PSFG. Okay, so this is our P1, and P2, which is open to the air, gonna be 0, and we're given the Q equals to 5 cubic feet per second. The head loss is 9 feet, and from the figure we know A1 equals to 0.8 feet squared, A2 which is 0.2 feet squared. Okay, and the difference of the 0.1 and 0.2, delta Z is 12 feet. Okay, so we're gonna apply the energy equation between the 0.1 and 0.2. So P1 over gamma plus V1 squared over 2G plus Z1 is equals to P2 over gamma plus V2 squared over 2G plus Z2. Okay, so apparently we know the P1 and Z1 is 12 feet, Z2 is 0, and we're still missing the velocity for section 1 and 2. So, but we do have the discharge, so we're gonna find Q A1, so that's your V1, which is gonna be 5 cubic feet per second over A1 is 0.8 feet squared. So this will give us 6.25 feet per second. And the V2 is also equals to Q over A2, which is 5 cubic feet per second over the area, which is 0.2 feet squared, which is 25 feet per second. Okay, so now we're gonna apply all the numbers into the energy equation. So P1 is defined to BF per feet squared. And the gamma is 62.4 lbf cubic feet. And we need to times 0.8 because of the specific gravity of the gasoline is 0.8. And V1 is 6.25 feet per second. 2 times 0.2. And Z1 minus Z2 is 12 feet, which equals to P2 over gamma plus V2, 25 feet per second to the power of 2 times the G. Okay, so, and gamma here is still 62.4 F per feet, cubic feet. So now I'm gonna solve this entire equation. We will have P2 equals to 2,287 PSFG, which equals to 15.9 PSIG. Now let's look at 7.25. A reservoir with pressure is pressurized as shown. The pipe diameter is 1 inch, so D equals to 1 inch. And the head loss in the system is given, which is 5 times the velocity to the power of 2 over 2g. So the height between the water surface and the pipe, so it's from the water surface from the pipe, delta Z equals to 10 feet. And discharge here is 0.1 cubic feet per second. So the problem is asking us what is the pressure in the reservoir. We're gonna assume alpha equal to 0 at all, equals to 1 at all locations. So given the information here, we can write down the energy equation between point 1 here at the water surface and point 2, which is at outlet. So P1 over gamma plus V1 squared over 2g plus Z1 equals to P2 over gamma plus V2 squared over 2g plus Z2 plus head loss. So P1 is pressurized, so it's not 0. V1 is 0 because it's the water surface, so it's stationary. Z1 is the 10 feet. P2 is 0 because it's open to the air. V2, we still don't know it. And Z2 gonna be 0 if we set it to be 0 and Z1 equals to 10 feet. And head loss equation is given here. So then we can simplify the equation. P1 gamma plus C1 equals to V2 square root over 2G plus the head loss is 5 V2 square root over 2G. So the V2 is equals to the V, because we only have one velocity in the entire problem. Okay, so the next step, we're gonna find the V2 we need. So V2 equals to Q over A2, which is, the Q is given 0.1 cubic feet per second. And A2, we're gonna use the diameter, which is pi over 4 times, because it's in inch, we're gonna convert it to feet, 1 over 12 feet. So our V2 gonna be 18.33 feet per second. So now we can substitute that into our equation. P1 over gamma, which is 62.4 BF over cubic feet, plus C1 is 10 feet, equals to 6 times V2, 10.33 feet per second, over 2G, which is 32.2. Okay. So our P1 gonna be 1329 pounds per square feet. For 7.31, we have siphon the elevations at point A, B, C, and D are CA equals to 30 meters, CB equals to 32 meters, ZC equals to 27 meters, and ZD equals to 26 meters. And the head loss between the inlet and point B, so we call that head loss 1, is 3/4 of the velocity head, so something like that. And the head loss in the pipe itself between point B and end of the pipe, head loss 2 is 1/4 of the velocity head. Okay, so for those conditions, what is the discharge and what is the pressure at point B? So the pipe diameter is 25 centimeters, which is 0.25 meters, and alpha equals to 1. So for this problem, we have 4 different points. So to find the discharge, we need to find the velocity in the pipe. So we're gonna choose point A and C for our elevation, so for our energy equation first. So PA over gamma plus VA squared over 2G plus ZA. The reason we choose those 2 points is because they are very easy to find the velocity, because the pressure at 2 points gonna be 0, and the velocity, because they are the water surface, so it's also gonna be 0. Okay, so as I said, the pressure is 0, the velocity head is 0, so leave us only the elevation difference and head losses. So ZA equals to ZC plus the head loss. Okay, so ZA is 30 meters, ZC is 27 meters, and you will find head losses. Which is the 3/4 plus the plus V squared over 2G plus 1 of the velocity. So you might notice we are adding the velocity head here in the head loss, because actually when you look at the problem, the outlet of the pipe is not open to the air, and actually it loses all the velocities when it was submerged in the lower reservoir. So that's where you lost the entire velocity head. So here in the head loss term, we need to add that term to the equation. So if we keep simplifying it here, so it will be 2 squared over 2G. Okay. So now we can find the velocity. So V gonna be equals to 5.42 meters per second. So now we have the velocity. We can find the discharge at point B. Okay. So Q equals to V times A, and diameter is given, which is 0.25 meters. So the discharge is gonna be 0.266 cubic meter per second. So now we have the discharge. The last thing we need to find is the pressure at point B. So we can either choose the point B and A or point B and C to apply the energy equation. So for here, we're going to use point A and point B. So we write down the energy equation again. Plus V squared over 2G plus ZA equals to PB gamma plus VB squared over 2G plus ZB plus the head loss. So it's the same as the first energy equation. The pressure and the velocity of point A is 0 and ZA is given, and PB, we still don't know it. The VB is actually equals to the velocity we found inside the pipe. And the ZB is given, and the head loss is 0.75 v square over 2g. Notice here at point B, you still have the velocity head. It was not dissipated at the end of the pipe. Okay, so CA is 30 meters. Goes to the PB gamma, which is cubic meter plus the VB, which is equals to the V. G 2 times G. So using SI unit. And CB is 32 meters. And the head loss is 3/4 of the velocity head. So PB gonna be negative 4.62 meters over which is equals to actually it's times 4 meters times newtons per cubic meter, which is negative 45.3 kilopascal. So because the point B is higher than the point A, so you will have a negative pressure at point B. Now let's look at 7.40. A water discharge of 8 cubic meter per second is flowed through this hollow dumper pipe. And diameter is 1 meter. The head loss is given, which is 7 times the velocity head. And the problem is asking how much power will have to be supplied to the flow by the pump to produce discharge. So for this problem, we're gonna use the energy equation first to find the power head. Then we're gonna use the power equation to actually find the power we need. So let's first write down the energy equation between the point at the water surface and the point at the outlet. Okay. So P1 or gamma plus V1 squared over 2G plus Z1. And from point 1 going through the point to the point B will go through the pipe. So the pump head will be on the left side. And the water the head losses will be on the right side. 2 squared G. So the P1 is equals to 0 because it's open to the air. V1 is also 0 because it's water surface. And Z1 is given, which is 40 meters. And P2 is also equals to 0. V2 is the velocity of the pipe. Z2 is given, which is 20 meters. And head loss is also given, which is 7 times the velocity head, which in our case it's V2. Now we write down the numbers. So V2, we don't know it, plus C2 which is 20 meters. Hair losses is 7 times V2 squared over 2G. So we need to find the V2, and we are given the discharge equals to 8 cubic meter per second, and we can easily find V2 equals to Q over A2, which is 8 per second. A2 is pi over 4 times the diameter, which is 1 meter. So V2 equals to 10.2 meter per second. Okay, so now we can plug the V2 here. So P equals to 8 times the V2. The elevation difference is minus 20 meters. So the power head is 22.4 meters. Now we're gonna use the power equation, which the power equals to the Q times gamma times the power head. So Q is given, which is 8 meter per second times the gamma times the head, which will give us 1.76 million watt. Now let's look at the last problem, 7.47. So we have a hydraulic power system here. The elevation difference between the water surface to the water surface downstream is 24 meters. The velocity of water exhausting into the pond is 7 meters per second. So we'll have head loss here equals to V 2G, which the V equals to 7 meters per second. And we have the discharge of the system equals to 4 cubic meter per second. And the head loss due to the friction in the penstock is neglectable. So the question is asking us what is the power produced by turbine in kilowatt. So we're gonna write down the energy equation for this problem. We're gonna set the higher water surface as 1 and the lower water surface at 0.2. Okay, so P1 over gamma plus V1 squared over 2G plus Z1. And this is turbine, so the head for the turbine is gonna be on the right of the equation. 2G. So we're gonna have the head of turbine HT and head loss both on the right side of the energy equation. So for this problem, the P1 is 0, V1 is 0, P2 is 0, V2 is 0. So we only have the elevation difference and the head losses and the head of turbine. So, okay. So, if we set the Z2 equal to 0, then Z1 will be 24 meters, and we'll have the turbine, which is HT, plus the head loss, which is V squared over 2G. Okay. So the head of turbine equals to the velocity, which is given 7 per second squared over 2 times the G. Meters per second. Plus the 24 meters. Okay. So the head of turbine is 21.5 meter. So now we're going to use a power equation to find the power of the turbine. P equals to Q times gamma times the head of turbine, which is equals to Q is given 4 cubic meter per second times gamma, which is 9,810 Newton per cubic meter times the head, which in the problem asking us to put that in the kilowatt unit. So it will be 844 kilowatt.